Okay, all right. So before we continue with ancillary services, right, two things. One is homework 6 is out. It's very short, so two quick questions shouldn't take you all that long to do. All right, so the reason there's a homework that's due next Wednesday is the final is next Thursday, Friday, right? So, at least one question from the homework will be similar question to the homework will be on the final. Right? Okay. So again, the final will be released on Thursday, due Friday night. That's probably about 6 to 7 questions. Altogether will take you 2-3 hours to do the final. Right? If you do all in one setting. Okay? So plan accordingly for those 2 days. Any questions on that? Okay, all right, yeah. But because it's a final, there will be no extensions, right? So it's once it's released, it's just due Friday night. And all right, so the final again will cover up to from the beginning class to the type of questions that's on homework 6. Right. So it's all are possible. Out of those, I'll pick 6 or 7 questions that be on the final. All right, so again, for the final, there will be a lot of optimization problem asking you to solve. Again, show your work. Okay, show your work. The only thing you can say that we use something to solve this, and the result is when you get to a system linear equation. Okay, as you get there, you can just declare what the solution is. Otherwise, you have to show the steps. Okay, so it's not enough to just say this is the optimal solution for the problem. Right? So it doesn't matter if that happens to be true, but you have to show your work for this. Okay. Okay, so then let's continue with ancillary services. Right? So ancillary services is the last major part of the power system economics. Right? So power system market. Right? So in the market, again, you have to buy generation to meet demand. Because things go wrong all the time or unplanned things happen, you have to get something so-called ancillary services. And so the question is, one is how much should you buy? How much, who should pay for this? And how should you pay? Right? So we're going to take a look at these things. And so ancillary services, again, the key thing is that you're buying things that you may not use, right? You're buying things that you hope you don't use. And so from a generator perspective, then if you offer things like reserve, then those are not energy, right? So you have opportunity for a generator. You have to decide: do you want to sell yourself into the energy market, or do you want to sell into the reserve market? So typically you cannot do both. Okay, so if you're a generator, you have a 100 megawatt limit. Your energy plus reserve cannot be more than 100. So you have to think about which part what do you want to sell. So the actual setting of ancillary services can be extremely complicated. Okay, so this can be complicated as a complex optimization problem. We are not going to really think about how much ancillary service you should buy. We're going to say that the operator somehow determined this, and then let's see how you're paid if this is the amount of ancillary service you need. Okay, so determining how much ancillary service you need for a system is extremely complicated. There's often you run very large simulation studies to determine this. So when we do a problem, we show you a number. Think out this number came out as kind of simulation studies. Okay, we determine that's a number that will cover all the incredible contingencies. Okay. So if the amount is decided, again the question is, how do you get this amount? Right? So let's say I have a system, I decide I need a gigawatt of ancillary services. Where do I get this from? And there's basically 2 approaches. One is compulsory. So compulsory means that you're just required to do this. Right? It's not a market. If you're in the system, you have to do ancillary services. Another approach is the market. So both of these are used. Actually, even in a single system, both of these are used. The reason is both have drawbacks and advantages, right? So you have advantages and disadvantages for both of these. So your choice is really determined by a number of things. So one is the type of services. Okay, so are you buying frequency regulation? Are you buying very fast reserves? Are you buying spinning reserves? Are you buying non-spinning reserves? What kind of reserve do you have? So that's a type of service. There's the nature of the system. Okay, so nature of the system means what kind of generation do you have in your system? Now determine how you buy reserves. Okay. Right, so to think about this, let's say you have one system that's predominantly hydro, like us. One system that's predominantly gas and coal, which think of that being PJM, okay, or Florida systems are like that. So which of these systems, one that's mostly hydro or one that's mostly gas and coal, which ones do you need more ancillary service? Or does it matter? Right? So I have two systems. You compare something that's hydro and something that's mainly, say, coal. Would you want to require different amount of ancillary service, or would you want to buy different amount? Which of this system is easier from a reliability perspective? Okay. Right. So this actually, so the answer to that, it depends. So the coal and gas system is easier to do frequency response. They're faster, they can do faster frequency response. But it's harder for them to do non-spinning reserve. So there you need a market to get non-spinning reserve. You need things that can fire up, right? So non-spinning reserve, it doesn't mean that gas cannot ramp up in 20 minutes. As your gas generator, you'd rather be selling energy rather than sitting there doing non-spinning reserve. So there it's sort of harder to get non-spinning reserve that way. So you run a market. If your system now you're hydro, you don't really worry about non-spinning reserve. Hydro systems are tremendously large storage systems. That takes a while to turn on, but once it's on, you don't give hydro system half an hour, it basically act like a storage over that time scale. But the frequency regulation is harder, it's a bit harder. So you need to worry more about frequency regulation. So really determined on the nature of your system, what generation mix you have. So different systems operate a bit differently in all of this. And then it's also actually dependent on history. Okay, so sometimes just historical choices that you always operate one way. So the thing to remember is both of this can happen. And typically both of them are present even in one system operator's control area. Right, so compulsory is sort of the easier way to do this, right? So it says if you're connecting to the system, you have to meet some conditions. The typical conditions you have to meet is 4% troop. Okay, so this is typical requirement says that however much you're generating, you need to have an up and down 4% possibility to change for frequency control. So that's you're not going to pay for this. This is basically you clear the market for energy, and whatever you're doing, you need up and down 4%. Right? This is a requirement for the system to be there. So this is for frequency. Typically, you also have a voltage requirement. So if you don't know what this means, it's okay. But you also have this generator needs to operate from 0.85 lead to 0.9 lag. Okay, so if this means nothing to you, that's fine. But if you know voltage control, then this basically saying you need to be able to change your reactive power. You need to be able to change your power factor to be in the system. This sometimes done in a market. Reactive power is almost always a requirement. Okay? If you're in the market, you just have to do this. Okay? This is normally not a market that's run here. Okay? So the advantage here is, right, so any questions with this kind of practice, with this? Again, these are typical numbers. Different systems will have slightly different things, but this is an example. Okay, so a question for you is, how do you validate this? Okay, so your generator, if you are a generator, you tell system operator, I'm providing you 4%. I'm doing this. Is there an easy way to tell whether the generator is actually doing this or not? Is there a way to validate the generator doing whatever they're doing? So it turns out there is not. So if you know Daniel Tavis, he spent a summer for Kaiso checking this. They have many, many generators. Kaiso's belief is actually many of them is not meeting this. They were simply not doing the job they're supposed to do. That turns to be extremely hard to determine what exactly they're doing. And then his job was running sort of some data-driven algorithm to figure this out. I don't think they have a very clear idea. Okay, so this is compulsory. In sense, you have to do it. It's sort of hard to check in the field whether what you're actually doing once you're generated. It's not easy to check this. Okay, but the advantage is it's just easy. Okay, at least from a market rules, from a sort of rule perspective, it's very easy. You just put a number to it, however you do it. Okay, and this this yearly insurance system security. What this means is because you are setting, or the system operator is setting these numbers, you can pick whichever one you want to get the security you need. Okay, right? It's up to you to pick. So there is not a question of what if not enough people respond. Okay, so if you make a rule that when they come in, they have to do this, then that's fine, right? Then you're meeting security. You can always meet this. Okay. So what are some of the drawbacks? What are some of the disadvantages of, say, enforcing people how to provide this kind of service? This actually comes out for renewable. If you think about it, you're being forced to do all these things. As a beneficial to renewable integration. Okay, right, so the disadvantage is one drawback is this is not good economic policy. It's good for system security, but it's not good for economic policy. One is because not all units need or even can provide ancillary service. Okay, so it's that they may not have the capability of doing this, right? So if you think about voltage control, for example, if you're a wind turbine, let's say if you're type 3 or let's say you're type 2 wind turbine, there is no way for you to provide voltage support. If you're right, so that's just not possible. Then if you say that you have to provide this kind of service to be in the market, then you squeeze out some units. Okay, so this may be overkill that you are discouraging some units to be in here. And for a while, this was actually a barrier to technology. Okay, so it's barrier to technology innovation because again, for solar and wind, it's hard if you're operating solar to say you always give me 4% juke. It's even harder to say you can do voltage. You can have this large of a reactive power range to do this kind of voltage control. This is quite difficult for something like solar, or it used to be quite difficult, something like solar. You're basically asking that your reactive power needs to be almost as large as your active power over all your operating conditions. This is challenging to do. So if you insist they have to operate this way, you're basically squeezing out some of the new technology that you precisely want to be in the system. Okay, so you're creating some barriers. You're basically asking things to be done however that have been done before. Right? So not all gen units need to do this. They may not be able to do this. And sometimes they're providing a costly service for free, right? So they're providing. And so there are some inefficiencies that comes in with this. Providing reactive power for things like generators can be costly. This doesn't account for that. They just require you have to do it. So that gets then well, of course, the generator takes that cost, built into its active power cost, and then that creates market inefficiencies because it has to get this money somewhere. So create an inefficient active power sort of cost. Okay? So that's a disadvantage. And there's sort of other things that comes out. This is a big equity issue. So there are some generators that just cannot provide services. This doesn't, for example, wind and solar is difficult. Also, there's something difficult as nuclear. Okay, so nuclear plants doesn't do frequency response. It's not fast enough to operate within a second to respond to frequency. Okay, so what this kind of compulsory rule is, it sounds good that everything has to do, 4% or 5%. But when you look at it, half of your generators can do it. Then you create special rules for those generators because you want them to be in the market. Okay, so this is the problem with compulsory provision. As if you create the this rule and it doesn't meet the technology, then what do, right? So you either squeeze this generator out of the market. Nuclear for many systems is too important. They have to be in the market. Then you create different rules. You create special rules for them, right? So then you lose the point of having compulsory markets. Okay, so that's the reason why, again, in the last 20 years, there's a big push to move to markets instead of forcing people, instead of having constraining people what they have to do as you move to markets. And really what we have been doing is different markets for different services. Okay, so for things like frequency regulation, things like those things, you have what's so-called long-term contracts. So for things like frequency regulation, you're always doing this. You're doing this for every second of every day. This really doesn't depend on which day you're talking about. So what you do is just contracts with people. So say do frequency regulation for the next 10 years, right? You got paid this much because you're doing frequency regulation. Okay, so if you cannot do this, you don't sign a contract. If you can do this, you figure out what the contract value is with the system operator. So that's one example. Can you think of another example where it makes sense to sign long-term contracts and say not run a day-to-day market? The frequency regulation is something that happens on a very fast time scale that you always need. And there's something that's on the sort of opposite end of the time scale that also makes sense to sign long-term market. And what are some of the rare events that, anybody remember? If you have a total system blackout, what is a starting generator called? Remember the name for that? Black start, right? So on the other spectrum as something called as a black star capability. The black star again means that you have complete blackout, and you have the ability to restart the entire system. Okay, you can maintain frequency, you can maintain active reactive power, you can just start. This is again a long-term contract, right? This doesn't make sense to bid who's a black star generator every single day. You basically say you demonstrate you can do this, then you're gonna sign a long-term contract. And this is actually a very useful thing to have. You want to be a black star generator because that means you're always in the market. You are basically the unit that has to be always wrong because you can do black star, right? So every market has to clear you. So this is actually quite competitive fitting into this. Everybody wants to be a black star generator. So these are long-term contracts. We're not going to worry too much about these because this is where you just negotiate with the system operator, figure out what the number is. Okay, so there's not really a spot market that there's not a auction you run for this. It's just a negotiation. The spot market is something that changes day to day. So really what this means is there's something that depends on the demand. Okay, so if the amount you need for reserve depends on what the actual demand is, then you need to run spot market because this is changing. And this is typically the reserve. Okay, so the spinning or non-spinning and non-spinning reserve falls into this category. Okay, so for spinning things like spinning reserve, we may want something that's 10% of spinning reserve. That depends on where demand. So whether how much, so if your demand is low, you don't need that much reserve. Demand is high, you need more reserve. So this is coupled with demand. Unlike these two, this doesn't really matter what demand is for these two. So here you run a spot market. And then we solve this spot market day by day. So this is solved every day. You figure out what reserve is. And some generator from different times, you may be generating energy, you may be doing reserve, depending on what exactly you're doing in Spark. Okay, so this is, you can think of this run daily. Questions for this? Okay, we'll see how this is done later. We'll see how exactly do you run this reserve market together with energy. But the idea is there are sort of different services are handled differently in the system. So unlike energy, which is one market, reserve is really, there's a lot of different reserve services. If you go work for a system operator, again, you spend a lot of time thinking about different services you need for your system and coming up with different markets for them. Okay, so the advantages are sort of clear. The main advantage is economics, right? So you're more efficient, you buy what you need. Not everybody have to participate in this. And allows for new technology to come in, right? So if you need that technology, you're not competing against mature technology that does everything. If you do one thing better, you can be in the market. Right? You can pick and choose whichever market you want to be in. Good. So for this, for example, storage is very good at frequency regulation. Many frequency regulation markets in the world is basically all storage now. They're just so much faster than everything else. So much cheaper and faster than everything else. They are running frequency regulation. Okay. So what are some of the disadvantages of this market? Why might you not want to run this market? Right. So one is you don't know what the outcome of the market is. Right? So less certainty. So this has happened. It has happened in Europe where one day for some reason they were calling for reserve and nobody wanted to do reserve that day. So they actually cannot meet their reserve target. It was infeasible to solve the problem. Right? Then it's unclear what you do. That so if it's infeasible, nobody wants to do reserves, then what do you do? Okay, so that's one drawback of having a market. You can't always determine that ahead of time. There's another big drawback that people worry about whenever you run a market. Okay, so another big problem is there may be market power, especially with reserves. As if reserves sometimes you make a lot less money than energy, right? Just you're not being called. So there may be only a few players that's providing reserves. Then if one of them goes offline, right? Because let's say market power, then you may run into a situation again, you're not feasible. You don't have enough reserves. Or you have to pay a lot of money to get a reserve you need. And this comes especially because for reactive power, this can come up a lot. Okay, so because the way reactive power is produced and how reactive power is transmitted, there is a market for reactive power. People create a market for reactive power, but now it's very, very regulated. It's very easy to game the reactive power market. It requires some to game this. Right? So for people who knows reactive power, you can game this basically by running LC circuit. If you want, you run LC circuit, you can change the reactive power in the system. And then yeah, you can get into situations where you don't have enough reserve. Okay. So the thing particular one we'll look at is, so there's in early systems where you had with co-optimization of energy and reserve. So so we're going to look at co-optimization energy reserve, and people look at co-optimization because when we have very early energy markets around 2000s, was a sequential market clearing. What happened is you first clear the energy market, then the leftover generators got output into a second market to clear the reserve. Then that's leftover, right? So this is energy, spinning reserve, non-spinning reserve. Take all those, traveling to the market and clear that. Okay, so you keep this for sequential clearing. This got to be way too complicated, and people starting playing a lot of games about which ones to be in. So there's ways to create a case where this thing gets clear, this thing gets clear, this is extremely expensive, and you try to be here. So we don't do this sequential clear anymore. But today, what you do is you just put everything together, and you try to sort of centralizedly clear everything. Okay? So what we're going to look at is we're going to centralize market, we're going to clear both energy and reserve all in one shot. Okay? So the way we're going to do this, we're going to write out a constraint optimization problem and solve that problem, where the constraints will have both energy and reserve all together once. And we're not going to think of a sequential way, right? So we're not going to think that energy is more important or less important or has first priority. Today, you just shove everything into an optimization problem and solve this whole thing at once, instead of doing this sequentially. So let's look at an example. Let's look at the following example. So these things will become more clear if we go through this example. So this is a typical example. So I made the marginal cost constant for simplicity. But we can see, as you can see this kind of example, this says that I can provide this energy at this marginal cost. This is the maximum generation limit for each generators. And some generators can provide reserves, some generators cannot provide reserves. Okay, so we're going to write out a system where the energy has to meet the load, and you have to meet some reserve margin for the system. Okay, and we're going to figure out for each generator how much energy you should provide, how much reserve you should have. Okay, what is the balancing between energy and reserve given this type of market? Okay. Any question about the data? That's here. Okay, so why might this number be 0? Okay, so right? So why would let's say a generator not be able to provide reserve? So what kind of generator? Let's say I'm extremely cheap. I can provide a lot of energy, but not reserve. I cannot do reserve. Technologically, what limits you from providing reserve? Right. So something like solar and wind, where you cannot do reserve, or something like nuclear, where your ramp rate is very slow. Okay, so this is either right, solar or wind. You cannot really, you don't know what this will be. Nuclear, where you are very cheap for energy, you cannot ramp in 20 minutes. So you just declare I cannot do reserve. Something like this, for example, this may be coal, this may be gas, where you can ramp pretty fast, but you're more expensive. And so this is a made up type of generator. Really don't have this type of generators, but this is there's sort of different reasons why a generator may or may not be able to do reserve. They have different ability to provide reserves. So you can look at unit 2. So what happens is, so here what I'm plotting 2 or 3, this is energy you can produce. This is the amount of reserve you can provide. So they all look like something like this. As if you provide energy from 0 to 50, you can give 190 full reserve. Okay, you can do all your reserve. You can, this is called ramp limited. This means this is the max you can ramp in this time. You can provide reserve. If you provide more energy, you can provide less reserve. Okay, so as a generator, let's say for unit 3, this is the maximum of 240. If you're providing 240 of energy, you cannot do reserve. Okay, you have no room to do reserve. If you say providing some energy here, this is the amount of room you have for reserve. Okay, so it's important to remember the constraint is that the energy you're providing plus your reserve cannot be bigger than the maximum energy you can provide. Okay, so energy and reserve are not separate things of the generator, right? So if I'm showing you a table like this, it doesn't mean I have 230 of power plus 160 of reserve. This just means together, the power you produce and the reserve you provide the summing up cannot be larger than 230. And the reserve itself cannot be larger than 160. Okay, so that's what this graph is showing. Okay, it's not separate things. You're a generator, you're providing power as a generator, right? So energy and reserve are coupled together in this kind of generator. Any question with this concept, this graph? And so that's typically where the hardest concept is. Good. But what determines the value for ramping? So I just made up this number, so this is just a number I made up, right? So for example, let's say again you look at unit 3, right? You have 240 of maximum power generation, 190 of reserve. So what this saying is that suppose you are operating here, then you ask for reserve. What's limiting you is in the next 15 or 20 minutes, the maximum you can rent is 190. Okay, so you cannot go faster than 190. So the maximum amount of reserve you can provide is 190. Okay, so that's called a ramp limit. Right, so you're not running out the maximum generation capacity, just you can't ramp that fast. If you go here as you can ramp this, but you're just running out of capacity. So this is called a capacity. So headroom, it means capacity. How much capacity have you generated? Okay. Any other questions? Okay, so this is again, you're providing energy and reserve at the same time, right? So we're gonna set up this market. So we're gonna assume that the market is perfectly competitive. We're gonna assume that the generator submits their bids for energy. And then the system operator will meet the demand, right? So we'll meet some demand while satisfying this reserve. Okay, so here we're going to look at what happens if you change your load between this sort of limit, between these two limits, 300 to 720. Well, you have to always meet this reserve requirement. Let's see the different dispatch that comes out this kind of requirement. Okay, so if your load changes, how you provide reserve, how you provide energy, how you provide reserve will change. Okay, so here we're going to look at where the load varies between these two numbers, and you have a reserve requirement. Any questions about this problem setup? Okay, so now let's take our break now, actually, because we're going to do this in one go. We'll write out this question and look at how to solve them. So let's take a 5-minute break, then we'll write out the optimization and then solve the problem. Let's see what's going on here. All right, okay, so let's look at how you write this into optimization problem. Okay, so it changes the problem we had before a little bit, because what changes is now you have a lot more decision variables. Not a lot more, but you have more decision variables. Right? So you look at the decision variable, the variables you're optimizing over. So this be the power generation. So you have P1, P2, P3, P4. So you have these are the decision variables. In addition, you also have the reserve. Okay, so R1, R2, R3, R4. Okay, so you're not only optimizing over power, you're optimizing over reserve. You're optimizing over both together. So what are the objective function? So this is given by the cost multiplied by power. So the objective function comes given by the price multiplied by power. So the cost is 2 times P1 plus 17 times P2 plus 20 times 3. Okay, so you're trying to minimize this number. Then we have a bunch of constraints, right? So we have the first constraint is our load balancing constraint equals to demand, right? So the power you generated has to be equal to demand. This is constraint. How do I write the reserve constraint then? How do I write the reserve requirement? Okay, so I have a power constraint, but let's say my reserve needs to be always be this level. How do I write that as a constraint here? What kind of constraint will reflect I have a reserve of 250 megawatts? Equals to 250? Right? So you want to be at least 250, right? Right. So this is actually, so the important thing here is you cannot write this equal to 250. What you want is you want this to say, I want at least this much reserve. Okay. So for load, this is equal sign. Load is your power generated must equal to the load. Okay. For reserve, it's different because you're not using the reserve, right? It's a requirement, it's something being called if something happens. So having 250 megawatt reserve is larger than or equal to some. You can do 250. You can be bigger than 250 as well. This sometimes makes a difference, actually, having more flexibility on this side. Right? So this is a reserve constraint. So again, difference is this is actual power being transmitted in the system. This is what's left over that can be called. Right? So there's just a difference there. Right, so this is your two constraints here. And then these are the reserve constraints, but of course you have the generator limits, right? You have the reserve limits now, because not every reserve, not every generator can provide reserves. So you have some limits on R1, R2, R3, R4. So the limits will be R1, it doesn't provide reserve, so it will be 0. R2 can go between 0 and 160. R3 can be 0 and 190. R4 doesn't provide reserve. Right? So this is a reserve that these generators can provide, and they're bounded between these ranges. Right? So if it's 0, we're just writing R1 equals to 0 here. That's fine. Okay, so then with these, as now you have the limit capacity on the generator. Right? So you have as for the first generator, again, together, the power and reserve together cannot be more than this limit. Okay, so this is 230. Right, so these are the limits. Goodness, limits reflect that you both, if you're a generator, you're providing both power and reserve. Okay, so this is the total when you sum. This is the limit. So that's the coupling constraint between power and reserve. Okay, so of course you have the P1, the sort of non-trivial, the more trivial solution. Right? So the power has to be all larger than 0, and together when you add them, they have to be less than this total generation. Okay, so these are your constraints in your problem. Given different demand, you can solve this constraint optimization problem to get what P and R is, right? So you take this is now your problem. Given demand, we have seen this before, right? So this is a inequality constraint, inequality and equality constraint optimization problem. You can solve, in principle, you can solve this and get the result. Right? So in your homework or the final, you will not be asked to solve something this large. There's a lot of choices. For most times in your homework is would be obvious how you do this or what the values are, but this is the principle way of doing this. Okay. Questions about this formulation? Okay. So how do I get prices out of this? How do I get the price for energy and the price for reserve? Where do I price, right? So I need to compute the price, right? You're paying people. So you're solving this. Let's say you solve this problem, you got some numbers for these. You got pay people, both for energy and reserve. Okay, so how do you compute the prices? How do we always compute the prices for this? How do we compute the price for energy? For this one. Right, so Lagrangian multiplier for this one. How about reserve? Reserve just Lagrangian multiplier for this one. Okay, so this is how the market's actually constructed. You write out the optimization problem, you look at the constraints not associated with demand and reserve. And then these are sort of by definition the prices you have. Okay, so you solve the problem, you figure out the Lagrangian multipliers for both of these two. Those are your prices. Okay, so let's say lambda, the multiplier associated here, the price of energy. Let's say the mu Lagrangian multiplier get here is the price of reserve. Okay, so this is the sort of the definition in some sense of our markets as to how you get the prices out of it. Okay. So the market works. So when you in practice, when you say I'm setting up a power market or I'm introducing new products into the market, what you're doing mathematically is you're creating a new constraint, and you're interpreting the Lagrangian multipliers out of that constraint as the prices of a new product. So that's mathematically what you're doing. Okay, you can talk of, so you think about whatever product you need to be able to express it into a constraint. And then the associated multipliers out of the constraint is your price. And so that's how all this sort of product works. Okay. In this case, everything's linear, so it's well defined. It's not linear, it's a lot more work to get that thing to define the prices. But still, that's how we think about it. Okay. So if you write down this problem, this is just a big linear programming problem, right? So you're minimizing the cost subject to a bunch of constraints, right? So in practice, really what you do is you get your computer to solve this. That's not very hard to solve. Okay, right? So you get a computer to solve this, you read out the multipliers, and that's your price. Okay, so we're gonna look at this solution by hand a little bit. We're gonna look at the solution by hand. Okay, so this is constructed for the solution by hand to be a bit easy. Okay. So how we go solving this thing by hand? As first, so in your homework and in your final, the problem will be constructing in such a way that you can solve this thing by hand. Okay. So for this problem, what you should observe is unit 1 is the cheapest and it cannot provide reserve. So what do is you always dispatch this guy to provide all the energy you need. So this set out to be this way: is you use this to provide all the energy you need. And then you can reduce the constraint. You can looking at reserves, you can think about different reserve constraints and different power constraints. These two are the only two that can provide reserve. These two are the only two that can provide reserve. So together, you have three constraints on reserve. You have a lower bound on the sum. You have an upper bound on how much each of them can provide. Okay, so any questions on this? Okay, so how do you get this number? Is even if R2 is at its maximum, you still need 90 from R3. Right, so that's just making this constraint a bit easier to work with. You still need 90 from the other generator to get to 250. Even if R3 is 190, you still need 60 from the other generator. So you can summarize these into this form. Okay, so this is your summary. And then what tells you is this induces a small lower bound on the power generation. Okay, so we're changing demand. We're looking at for how much each generator should generate for the demand. So our sequence will always be you dispatch this thing first. Then how much do you have left over? So P2 is second cheapest one. How much do you have over in P2? You don't have 260, right? You don't have 230 left over. You only have 170 because of the reserve requirement. Okay, so it's as if your generator got smaller because you have reserve, right? So when we have different demand, so we right. So what you have is you're basically shrinking how much you have, and then for each demand, I'm going to read this out. Okay, so this is the easy way to do this is the way to do it by hand. In your homework, you'll be repeating this thing by hand. And you can look at who's the cheapest one, how much, given this reserve requirement, how much generation do you need? So this shrinks your power generation ability, then you dispatch this in sequence. Okay, just read out this thing in sequence. Right, so now remember our load. We're going to look at what happens if your load vary between these ranges. So given different range of load, the behavior is different. So let's say my load is between 300 and 420. Okay, so let's say this is the load, right? So how will you generate? Is first you get unit 1 to produce 250. This is always the case. Okay, so unit 1 just provides 250. Then unit 2, so unit 2 is the cheapest generator after this one and has a limit from 0 to 170. Okay, so this is where the 420 range came out. As you add 250 to this unit 2's range of 170. Okay, so being within this range, as we have as unit 2 produces the rest. Okay, so as a second cheap generator, we have enough capability to provide the rest of the energy. So you just produce the rest up to 420, up to whatever you need. What is the marginal cost for energy here? What is the marginal price for energy? So unit 2 is producing the rest. Okay, so unit 2 is a marginal unit. So here the price for energy is $17 per megawatt. Any questions about this? Okay, got it. Right, so if it's exactly equal, you take the lower one by convention. So right, but that never happens. Basically, that's what never happens. Yeah, if it's exactly equal, you take the lower one. I forgot actually which one you take. There's a convention that you take. Yeah. But any otherwise, any questions? Okay, so the more interesting question is, what is the unit price of reserves? What about reserves? What happens to reserve? What is the unit price for reserve in this case? I need 250 of reserve, okay, within this range. So I dispatch generator one, I dispatch generator two up to its limit of 170. Do I need to pay anything for reserve? Does the reserve have a price? Right. So the way I always think about this, right now I'm asking for 250 megawatt of reserve. Suppose I ask 251 megawatt reserve. Does anything change in all this? Right. So in this case is so this can do 190 of reserve. This has 90 units of reserve left over. So the total reserve that's available in this case, because you did not call on generator three, so generator three has the entire 190 that's left over. Okay? This has the entire left over. You went up to the 170 range, but there's sort of 90 left over, right? So what there's yeah, so you did not call on this thing. You did not call on this guy. And then for anything that you have is basically plus the power generation from two P max to minus P2. This is larger than 250. Right. So except as a corner, other than exactly 420, if you look at the leftover capacity here for generator two, plus the capacity of generator three to do reserve, this added together is larger than 250, larger than the reserve you need. Does this make sense? Right? So it's larger than 250. So if this is exactly larger, what's the Lagrangian multiplier? For inequality constraint, that's exactly large. That's not tight. Zero, right? So the Lagrangian multiplier here is zero. So you have the price for reserve is actually zero. It doesn't cost you anything for reserve here. Okay, so the price of reserve is zero. Okay, so you're providing the reserve sometimes, in some sense, automatically for the system. Just by being there, by having this kind of parameters in the system, you will have enough reserve. There is not a tension between providing energy and reserve. So reserve is zero. This just happens automatically. All you care about the price for energy. Any questions about this? Questions for this case? Yeah, so it's very possible that for reserve to have a price of zero. Okay, unlike energy, which is determined by the marginal generator. And so if your marginal generator doesn't have a price of zero, it's zero. For this case, this is just zero. Okay? It's there. It doesn't matter whether you get it or not. It's because the generator are there, you have this reserve capability. Okay, so then this changes if your load keeps increasing, right? So let's say you go above 420, then what happens is your unit two is capped at 170. Okay, right? So unit two again, even though this seeming to say you have a maximum generator of 230, because you have to provide reserve, you appear to be a smaller generator. So you cap at 170. So here, unit 3 is marginal. Okay, so unit 3 is marginal. Then, so unit 3 being marginal, this means the price of energy is 20 per megawatt hour. Okay, so that's unit 3's price. So now the reserve is more interesting. Okay, so reserve is no longer there. So reserve now has a price. Okay, so think about the okay, so let's think about the reserve price. So reserve price means if I need to increase my reserve beyond 250, what happens? Okay, so let's say I increase my reserve a little bit beyond 250 to 251, let's say. Where does this 1 megawatt of reserve come from in this setting? Right, so how would I change what happens to unit 2 and unit 3 if I increase this reserve by 1 megawatt? Right, so I have to reduce the production of 2. Okay, so that's where I got the production from. Right, 3 is unlimited. I haven't hit the cap for 3 yet. So I have to reduce the production of unit 2 here. Okay, so then what I'm doing is you're swapping out a cheaper energy production with more expensive energy production. So you're trading off 1 unit of reserve. So 2 has to provide 1 unit of reserve. It can't provide energy anymore. So it has to provide you reserve. So the difference is 20 minus 17 equal to $3 per megawatt. Okay, so this is the total cost increase if you want 1 more unit of reserve, right? So you're reducing this is cheaper, right? So your cost goes down by 17, goes up by 20. So that's the difference. Okay, so if you solve this in linear programming, this is the marginal, this is the multiplier that will come out. But if you want to reason this way, this comes out basically because you're replacing cheaper energy generation with more expensive generation. Okay, this is, so you have $3 per, if you're providing reserve, you're getting paid this much. Because now reserve matters. Reserve energy is now coupled. Okay, because you hit this constraint. Right, so coupling comes because you're hitting this constraint, you hit this constraint, and this introduce a price for reserve. Any question about this? Okay, you're hitting this reserve price. All right, so then you can keep increasing this until a upper limit, right? So anything above 720, you actually cannot, it's not feasible. But between 470 and 720, this what happens is unit 4 is marginal. So then the price of energy is $28 per megawatt hour. Right, and now if you think about reserve, you're playing the same game again. If you need 1 more unit of reserve, what you do is you have to back off this thing by 1 and increase this generation by 1. Okay, for reserve. Right, so if you want 1 more reserve, as well, so this has to come out from the energy production of 1 of these. So you back off this one and you increase this one. So that's your reserve. Okay, so that's a reserve price. So this is the summary of price. Is if you're increasing your demand, then what happens is this is your reserve, it will jump like this. Then your energy also jumps at this corner point. Okay, each of this jump comes from the fact that you're hitting a constraint. Every time you hit a constraint, things jump, right? So prices are multipliers become non-negative, becomes strictly positive once your constraint is hit. So hitting constraints, you keep jumping until sometime you're infeasible. Okay, so this is the price and reserve calculation. So we're not going to compute the profit. There's a lot of, let's skip some of these computing profit, but you can go in and compute the profit for things generating both energy and reserve. So it can get fairly, reserve can make money depending on what else is happening in the system. So normally as a generator nowadays in the market is you go in and you bet your energy and reserve at the same time. Okay, so you tell the system operator, this is my energy production cost, plus I can do this reserve. And then the system operator clears everything at the same time. Okay. All right, any questions? Okay, so that's how things are done today. In the next, I guess, 10 minutes or so, we'll talk about sort of demand side provision. Right, so far until now, what happens is the generator provides reserve. The demand pays for this, right? So demand pays for everything in the power system market. If you're demand, you pay for whatever service is there. You pay for all the things, you pay for reserve, you pay for everything like that. And but the once people are talking about ancillary services, it's very quickly recognized that demand can also do ancillary services, right? Ancillary service just means that the net generation should be able, you should be able to cover the load, right? So generation has equal to the load. Then when something happens, it's equally good if I increase the generation or if I decrease the load. Right? So decreasing the load also, in some sense, provides ancillary services. This is a huge area of research and people trying to put into the market. It's basically demand response. Saying this demand should have some capability of providing services, then demand should get paid. Right? Rather than demand paying everything, demand should get paid given its capability of providing services. And often the benefit of talking about demand side response is demand customers are really small. Demand customers are extremely small. So you talk, instead of hundreds of generators, you're talking about millions of demands, right? The chance of them having any kind of market power is small. That's actually, in some sense, an efficient market. You can assume a large, very large N in the market size. So that's very large. You can think of this as better utilization, right? If you have, demands that's storage or electric vehicles or things that you can interrupt, now maybe a lot more sustainable than having half of a co-generator always being there just to provide reserve. So this is a lot more sustainable. And reliable or not, this is debatable. So the book sort of claim this is more reliable. It's sort of debatable how reliable demand side people are. They may or may not listen to you, but there's been talk about for demand type of services. Right, so for demand, there's one big type of service people can provide is interruptible load. This just means that something you're doing that can be stopped. They can interrupt the load. So for demand, your big loads, there are some load you don't want to interrupt. Some loads, things like lighting, you don't want to interrupt in the demand. Computing, you don't want to interrupt demand load. Other things like, dishwashing or HVAC or things like that, you can interrupt them, at least for a few minutes. It won't really be felt by the demand. So these are things you can interrupt. Demand can also do frequency regulation. This was a popular thing actually for about 10 years ago. What people figured out is normally for frequency regulation, you need something that's spinning. You need something that can at least give you a frequency. Okay? And then people figure out, hey, there's one example of demand that has a lot of sort of spinning load, spinning pumping load. Can you think of what this is? This is using one particular state in the US that has a lot of spinning load for DNS. If you look at Seattle, Seattle do not have much spinning load. Most load in Seattle doesn't spin. It's not synchronous. But there are actually some load in some part of the US that's actually quite similar to how a spinning machine will work. Can you think of this kind of load? Right, so think Florida. There's one type of load in Florida that's actually spinning and almost synchronous. So these are the pool pumps that people figure out. So if you're in the state of Florida, a lot of frequency regulation is done by pool pumps. There turns out there's enough people pumping all the pools there, makes a huge difference to the frequency regulation actually. So now what they all do is they are responsive to frequency. They measure frequency on the grid, and then they change their own speed. And that's quite a bit rotational inertia actually in the Florida system. It's not a small amount. Okay, so there's quite a bit there. So that's very specific to that one application. So most other places we do frequency regulation, see physics through inverters. So through power electronics can do this. Not, often not as well as pool pumps. These actually are really good synchronous machines. They are what you want us. They look very much like a synchronous machine when you model them. So power electronics can mimic this kind of situation. You can provide some of these services as well. Okay. So these are some of the demand side provisions. So for frequency, again, this is a bit easier for demand side to do. For frequency, is all you need to do is you do a little bit of change, as long as you're responsive to frequency. Even if you have a pool, you won't really notice it. This is sometimes you pump a little bit faster, sometimes you pump a little bit slower. You won't notice this as over a day. So frequency response is easier to do. Something like non-spinning reserve is much harder for demand side to provide. Okay, so because you have so many customers, you don't know whether if you call these customers a non-spinning reserve, will they actually do anything? Right? So you don't know what they will do, right? So demand side answer services, frequency regulation we're pretty good at. So this is more of a technology and control problem rather than an economic problem. This is as long as you can design the controller well, you can do this. For longer term ancillary service, longer time scale ancillary services is still a economic problem. If you really want people to be non-spinning ancillary service that's in the half an hour range, how do you pay people? How do you make sure they respond? That's not yet. That's sort of less of engineering problem, more of a economics question. Any questions about this? Okay, all right. So we'll end here today. So next class we'll look at some planning problems. We'll spend about half the class looking at planning problem. We'll spend the second half of the class looking at some reviews. We're looking at all the topics we cover and what might be on your final. Okay. All right, so take a look at the last homework. So again, it's short, but it does include a topic that might be on the final. Okay, thanks guys.